For over 160 million years, they reigned supreme. From the towering Brachiosaurus that grazed on ancient treetops to the lightning-fast Compsognathus darting through primeval forests, dinosaurs were the undisputed masters of Earth. Their world was a vibrant tapestry of lush vegetation, shimmering wetlands, and active volcanoes painting the horizons. Imagine vast plains teeming with herds of triceratops, their distinctive frills and horns a formidable defense against predators. Picture the powerful Tyrannosaurus rex, its thunderous roar echoing through the Jurassic and Cretaceous periods, sending shivers down the spines of all who heard it. This wasn't just a collection of giant reptiles, it was a complex, thriving ecosystem, a symphony of life playing out on a colossal scale. Every niche, from the deepest oceans to the highest mountain ranges, seemed to be filled by some incredible, specialized dinosaur. Life was abundant, and evolution had sculpted an astonishing array of forms, each perfectly adapted to its environment. The skies were not empty. Pterosaurs with wingspans rivaling small aircraft soared gracefully above, their keen eyes scanning for prey below. The oceans, too, were home to formidable predators like the Mosasaurus, a marine reptile of immense size and power that patrolled the ancient seas with unchallenged authority. This was a planet where the sheer diversity and scale of life were almost unimaginable to our modern minds. They had survived countless environmental shifts, volcanic eruptions, and fluctuating climates throughout their incredibly long reign. Their reign was so extensive that if you were to compress Earth's entire history into a 24-hour day, the dinosaurs would have dominated for several hours, a significant portion of the planet's timeline. They seemed invincible, an enduring testament to nature's power and adaptability. But even the most enduring dynasties eventually faced their ultimate challenge. The stage was set, not for a slow decline, but for a sudden, catastrophic end that would forever alter the course of life on Earth. A silent clock was ticking, and the golden age of dinosaurs was about to experience its most dramatic and final sunset. The forces that would eventually bring about their demise were already at play, hidden just beyond the horizon of their magnificent existence.
Yet, even in this era of unparalleled dominance, subtle shifts were occurring, almost imperceptible to the colossal creatures that roamed the land. For millions of years, Earth had been a volatile place, and the dinosaurs had adapted to countless geological upheavals. Continents were relentlessly drifting, reshaping ocean currents and altering global weather patterns. The supercontinent of Pangaea had long since begun its dramatic breakup, tearing apart into the land masses we recognize today. This colossal geological ballet wasn't just reshaping coastlines, it was profoundly influencing climates. Inland seas formed and receded, volcanic activity, though often localized, contributed to atmospheric changes, and vast forests, the very foundation of many dinosaur ecosystems, were slowly but surely transforming. These were not sudden, cataclysmic events, but rather the slow, inexorable march of geological time, each minute alteration accumulating over millennia. Consider the atmosphere itself. While rich in carbon dioxide, supporting luxuriant plant growth, there were periods of increased volcanic outgassing, pumping even more gases and ash into the air. This could lead to temporary cooling or warming trends, impacting vegetation and consequently the herbivores that fed upon it and the carnivores that preyed on them. The intricate web of life, though robust, was constantly being subtly rewoven. New plant species, like the emerging flowering plants, angiosperms, were slowly gaining ground, offering new food sources, but also potentially displacing older, established flora that formed the diet of many long-necked sauropods. These shifts meant that some dinosaur species, perfectly adapted to a specific type of forest or climate, might find their habitats gradually shrinking or transforming into something less ideal. It was a slow-motion environmental puzzle, with pieces constantly shifting. While the dinosaurs continued their seemingly endless reign, These underlying geological and ecological forces were subtly setting the stage. They were like the barely audible creaks and groans of a magnificent ship, sailing confidently forward, unaware of the treacherous waters ahead. The planet, in its constant state of flux, was preparing for an unprecedented event, one that no creature, no matter how dominant, could possibly anticipate or survive. The whispers of change were growing, though no ear was tuned to hear them, as the true magnitude of the impending catastrophe remained unimaginable.
The subtle shifts and whispers of change that had characterized the preceding millennia were about to be violently silenced. For 160 million years, dinosaurs had weathered volcanic eruptions, climatic shifts, and continental drift. But nothing, absolutely nothing, could have prepared them for what was coming. Imagine an ordinary day in the late Cretaceous period, a Maiasaura diligently guarding its nest, a Pachycephalosaurus butting heads in a territorial dispute, a Quetzalcoatlus soaring silently overhead, casting its colossal shadow on the forest floor. Life, in all its brutal beauty, continued as it always had. Then, without warning, the sky itself became an instrument of unimaginable destruction. From the blackness of space, an object of immense size and terrifying velocity hurtled towards Earth. It wasn't a meteor shower or a distant comet. This was an asteroid, estimated to be between 10 and 15 kilometers, 6 to 9 miles, in diameter, the size of Mount Everest or larger. Its trajectory was precise, a cosmic bullseye aimed directly at what is now the Yucatan Peninsula in Mexico. Traveling at speeds estimated at over 20 kilometers per second, 45,000 miles per hour, it ripped through the atmosphere, generating a shock wave that would have been felt globally even before impact. The air itself ignited, transforming into a superheated plasma trail visible across continents. The sheer energy contained within this celestial projectile was unfathomable, equivalent to billions of atomic bombs detonating simultaneously. The moment of impact was not just a collision, it was an apocalyptic event that defies easy description. The asteroid struck with a force so immense that it vaporized instantly, punching a crater over 180 kilometers or 110 miles wide and 20 kilometers, 12 miles deep. The surrounding rock, rich in sulfur and carbonates, was immediately vaporized and ejected into the atmosphere. A colossal plume of superheated rock, dust, and steam blasted upwards, piercing the stratosphere and even reaching into space. This initial explosion triggered a chain of devastating events. Global tsunamis, hundreds of meters high, raced across all the world's oceans, obliterating coastlines thousands of miles away. Gigantic earthquakes, magnitudes far exceeding any recorded in human history, ripped through the planet's crust, causing widespread devastation. The very ground trembled and buckled under the unimaginable force unleashed. Within moments of impact, the world closest to the impact site was incinerated. Any creature within hundreds of miles would have been instantly vaporized or obliterated by the blast wave. But this was only the beginning of the horror. The true, lingering devastation was yet to unfold, transforming a mere impact into a global catastrophe that would plunge the entire planet into an extended period of darkness and cold. The sky had fallen, and the dinosaurs, along with much of Earth's life, were about to pay the ultimate price. But how could a single impact lead to such widespread extinction? The answer lies not just in the initial blast, but in the insidious environmental cascade that followed.
The initial cataclysm of the impact was merely the opening act of a much longer, more insidious tragedy. As the colossal plume of vaporized rock and dust surged skyward, it carried with it billions of tons of debris, sulfur compounds, and soot from the ignited forests. This massive atmospheric injection didn't just reach the stratosphere, it spread globally, enveloping the entire planet in a thick, impenetrable shroud. Sunlight, the very essence of life on Earth, was effectively blocked. Imagine a perpetual twilight, or worse, an endless night. This was not a temporary eclipse. This was an impact winter. Temperatures plummeted rapidly. Without the sun's warmth, the Earth's surface cooled dramatically, plunging average global temperatures by tens of degrees Celsius. Photosynthesis, the fundamental process by which plants convert sunlight into energy, ground to a halt. In a matter of days and weeks, forests that had stood for millions of years began to wither and die. The delicate balance of the food chain, which had sustained these magnificent creatures for eons, was shattered. Herbivores, from the smallest browsers to the largest sauropods, found their food sources vanishing. Starvation became an immediate and widespread killer. The effects rippled outwards with terrifying speed. Without plants to consume, the vast herds of herbivorous dinosaurs began to perish. And as the herbivores died, so too did the carnivores that preyed upon them. A Tyrannosaurus rex, once the apex predator, would have found its world emptying, its primary food source disappearing. The sheer scale of death was unimaginable. Entire ecosystems collapsed, not due to the direct impact, but due to the devastating, prolonged lack of sunlight. Acid rain, formed from the sulfur ejected into the atmosphere, further poisoned the land and oceans, eroding calcium shells and dissolving delicate marine life. The world had become a barren, frozen wasteland, shrouded in perpetual darkness. This prolonged environmental collapse, rather than the immediate blast, was the primary mechanism of the dinosaur extinction. Those creatures lucky enough to survive the initial impact and its immediate aftermath faced a slow, agonizing demise from cold, starvation, and a poisoned environment. For months, perhaps even years, this winter of death gripped the planet, suffocating life and extinguishing countless species. The question now becomes, amidst such widespread devastation, how did anything survive?
Amidst the unimaginable desolation of the impact winter, a stark truth emerged. Not all life was extinguished. While the giant dinosaurs vanished, a select few lineages, remarkably, persevered. Their survival wasn't due to luck alone, it was a testament to specific adaptations, and in some cases, sheer chance in their ecological niche. Who were these improbable survivors, and what characteristics allowed them to weather a cataclysm that wiped out their colossal contemporaries? One key factor was size. Larger creatures require more food and are less adaptable to drastic environmental shifts. The immense body mass of sauropods and large theropods, once their evolutionary triumph, became their fatal weakness. Smaller animals, on the other hand, had lower metabolic rates, required less food, and could find refuge in burrows or protected environments. Many small mammals, ancestors of modern species, burrowed underground, insulating themselves from the freezing temperatures and the worst of the atmospheric fallout. Their ability to enter torpor or hibernation during periods of extreme food scarcity was also a crucial advantage. Another critical factor was diet. Herbivores were hit first and hardest as plants died in mass. Carnivores reliant on large herbivores quickly followed. Omnivores and insectivores, however, had a more diverse food base. Scavengers, feasting on the decaying remains of the dead, found a temporary, albeit grim, abundance. Animals that could consume detritus, seeds, or even fungi, which might sprout in the darkness, had a fleeting chance. This adaptability to a wider range of food sources was a powerful survival mechanism in a world turned upside down. Consider the birds. Descendants of small feathered dinosaurs, they were among the most successful survivors. Their small size, warm-bloodedness, and ability to fly allowed them to cover vast distances in search of sporadic food sources. Their diverse diets, including seeds and insects, provided resilience. While many early bird lineages perished, some adapted, evolving into the incredible avian diversity we see today. Similarly, crocodilians and turtles survived,
largely due to their ability to slow their metabolisms, enter aquatic environments for thermal stability, and endure long periods without food. Their semi-aquatic lifestyles offered protection from the direct atmospheric effects and provided access to aquatic food webs that, though damaged, might not have been as utterly destroyed as terrestrial ones. The extinction event acted as a brutal evolutionary bottleneck, clearing the stage for new forms of life to diversify. The survivors were not necessarily the strongest or the most advanced in the pre-impact world, but rather those with the most adaptable traits for a post-apocalyptic landscape. Their perseverance, against all odds, would reshape the future of life on Earth, paving the way for the rise of a new dominant group. But what would this new world look like? And how would these survivors capitalize on the emptiness left by the dinosaurs' demise?
The long, grim grip of the impact winter finally began to loosen. As the dust and aerosols gradually settled out of the atmosphere, shafts of sunlight, weak at first, began to pierce through the lingering gloom. The earth, scarred and barren, slowly started to thaw. This wasn't a sudden resurrection, but a painstakingly slow recovery that unfolded over thousands of years. Yet, in the wake of such profound destruction, a new world, radically different from the one that had existed for 160 million years, was emerging. The vast ecological vacuum left by the dinosaurs' demise created unprecedented opportunities for the surviving lineages. With the colossal rulers of the Mesozoic gone, the stage was now open. Mammals, once relegated to the shadows, scurrying underfoot, and largely nocturnal, suddenly found themselves with an open playing field. Their small size, adaptability, and warm-bloodedness, which allowed them to regulate their body temperature independently of the environment, proved to be enormous advantages. They began to diversify at an astonishing rate, radiating into countless new forms and ecological niches that had been previously occupied by dinosaurs. From tiny shrew-like creatures, they evolved into larger, more varied forms, exploring new diets and behaviors. The Cenozoic era, often called the Age of Mammals, was truly dawning. The surviving birds, too, underwent an incredible evolutionary explosion. Freed from the predatory pressure of large theropods and with vast territories newly available, they rapidly diversified into the myriad forms we recognize today. From eagles to penguins, from hummingbirds to ostriches, their ability to fly and exploit diverse food sources propelled them into a dominant position in many ecosystems. Even the surviving reptiles, like crocodilians and snakes, though not achieving the same grand scale as their dinosaur relatives, found new opportunities in their respective niches. The planet itself began to heal. New plant life, often different from the pre-impact flora, started to colonize the desolate landscapes. Forests gradually returned, albeit with a different composition. The climate eventually stabilized, though Earth would continue its long-term geological cycles. This new world, though born from catastrophe, offered a canvas for entirely new evolutionary narratives. It was a world where speed, intelligence, and adaptability, rather than sheer size, became the driving forces of natural selection. The absence of dinosaurs didn't just remove a group of animals, it fundamentally altered the entire trajectory of life on Earth, leading to the world we inhabit today. But how did we, as humans, come to understand such a colossal event that happened so long ago? The journey of discovery is as fascinating as the event itself.
For millions of years, the dramatic end of the dinosaurs remained a secret, buried beneath layers of rock and time. Their bones, fossilized remnants of a lost world, offered tantalizing clues, but the true cause of their sudden disappearance remained one of science's greatest mysteries. Early paleontologists, fascinated by these colossal creatures, could see a clear break in the fossil record, a period where dinosaurs simply ceased to exist, replaced by new forms of life.
But what force could have wrought such widespread destruction? For a long time, various theories were proposed, from prolonged volcanic activity to disease epidemics, or even a slow, gradual decline due to climate change. Each theory offered a piece of the puzzle, but none fully explained the sudden global scale of the extinction event. The breakthrough, a true aha moment in paleontology, didn't come from digging up more dinosaur bones, but from an unexpected source: geochemistry. In the late 1970s, a father and son team, physicist Luis Alvarez and geologist Walter Alvarez, were studying a thin, distinctive layer of clay found globally at the boundary between the Cretaceous and Paleogene periods, the precise point in time when the dinosaurs vanished. This layer, known as the KPG boundary, held a remarkable secret. They discovered an anomalously high concentration of iridium within this clay. Iridium is extremely rare in Earth's crust, but much more abundant in meteorites and asteroids. This discovery was a monumental piece of evidence. The Alvarezes proposed that the iridium layer was the fallout from a massive asteroid impact. The sheer amount of iridium suggested an object so large that its collision would have had catastrophic global consequences. Initially, this idea was met with skepticism. It was a radical departure from conventional geological thought, which favored terrestrial explanations for such widespread extinctions. However, further research began to provide compelling corroboration. Scientists found microscopic shocked quartz grains, tektites, small glassy beads formed from molten rock, and soot particles, all indicators of an immense high-energy impact and subsequent global fires. The final, irrefutable piece of evidence came in the early 1990s with the identification of the Chicxulub crater buried beneath the Yucatan Peninsula in Mexico. Geophysical surveys revealed a colossal, perfectly circular impact structure, precisely dated to 66 million years ago, the exact time of the KPG extinction. This wasn't just a coincidence, it was the smoking gun. The crater's size, its location, and the composition of the rocks within it perfectly matched the predicted fallout found in the KPG boundary layer across the globe. Science had, through meticulous deduction and interdisciplinary collaboration, finally pieced together the incredible story of the day the dinosaurs died. But what lessons can we draw from such a dramatic chapter in Earth's history?
The extinction of the dinosaurs, a narrative spanning 160 million years of dominance and ending in a single cataclysmic day, is far more than just a captivating ancient tragedy. It stands as a profound testament to the dynamic, often unpredictable nature of our planet, and it offers critical lessons for us, inhabitants of a relatively young epoch. What insights can we glean from the dust and bones of the Cretaceous-Paleogene boundary? Firstly, the story underscores the fragility of even the most dominant life forms. The dinosaurs, seemingly invincible, were wiped out not by a competitor or a gradual decline, but by a sudden external force. It reminds us that Earth's history is punctuated by periods of rapid, dramatic change, and that life, while resilient, is also vulnerable to forces beyond its control. This powerful reminder emphasizes the interconnectedness of all life and the delicate balance of Earth's ecosystems. Disrupt one fundamental element, like sunlight, and the entire edifice can crumble. Secondly, the event highlights the immense power of geological and astronomical forces. The Chicxulub impact was a stark demonstration that our planet is not isolated. It exists within a cosmic shooting gallery. While large impacts are rare on human timescales, the potential for such events remains a real, albeit low-probability threat. This understanding has spurred modern scientific efforts to track near-Earth objects, a global endeavor to identify and potentially mitigate future asteroid threats. The dinosaurs had no such warning system, no capacity to understand the danger hurtling towards them from the cosmos. Finally, and perhaps most importantly, the KPG extinction illustrates the concept of punctuated equilibrium in evolution. Rather than a slow, steady progression,
evolution can experience long periods of stability, punctuated by rapid bursts of change and diversification following mass extinction events. The demise of the dinosaurs cleared the evolutionary slate, allowing mammals to rise from obscurity and diversify into the incredible array of forms we see today, ultimately leading to the emergence of humanity. Our very existence is a direct consequence of that cosmic collision 66 million years ago. The legacy of the dinosaurs continues to fascinate and inform us. Their extinction is a powerful narrative of destruction, survival, and renewal. It is a cautionary tale about environmental vulnerability and a hopeful story about life's enduring capacity to adapt and innovate in the face of unimaginable adversity. As we look to the future, understanding this dramatic chapter in Earth's deep past helps us appreciate the delicate balance of our own ecosystems and our place within the vast, awe-inspiring story of life on Earth. The dust has settled, the silence has been broken by new sounds of life, but the echo of the great dinosaurs' final days resonates through time, a timeless lesson etched in the very rocks beneath our feet.